Welcome back to Pharma-info with Shubhashish. Today, the topic which we have decided, or rather I have decided, is the final form of 2D-QSAR. That is your Hansch analysis or Hansch equation, right? Hansch equation. Okay. But before dealing with this Hansch equation and all, okay, we'll just see another variables or another descriptors. Okay, that is called free Wilson approach. Free Wilson approach which deals with indicator variables. Indicator variables. Now, so we'll come to it later, but before that, we'll just see that what is the depiction of free Wilson approach, right? Okay. As I said, just beneath this I have written indicator variables, right? What is that indicator variables? So from the last couple of weeks, or rather in my last few videos, you might have gone through this the 2D QSAR, okay, or traditional QSAR. So there the basic aim was found to just relate certain properties of a particular chemical species to its biological activity. And we have seen that how this substituents, while being part of a particular molecular skeleton, they are influencing the biological activity, right? And we have seen that different parameters we studied, like your hydrophobic parameters, like your steric parameters, like your electronic parameters, and we have seen that each and every parameters, they're having a different thing to say. Okay, they are defining something about that particular molecular skeleton, right? Okay. Now, and these parameters are incorporated in the final form of 2D-QSAR. That means the Hansch equation, because the primary aim is, the aim to conduct 2D-QSAR is to generate, to develop a mathematical equation, right? And with that mathematical equation, we have to what? Unveiling the mathematical equation, definitely, or we are expecting that it can fetch us what? A novel compound, right? So this is the prime intention behind running this 2D-QSAR, right? Okay. Now let us just, so what we have seen that, so out of those discussion, we came across so many parameters and all, right? At least few parameters and all, and how these parameters are influencing the biological activity that we have seen. And each and every parameter, this like your, say for example, if we are just talking about hydroxyl group or an amino group, right? In a straight way we can say it is found to be, or it can contribute electronically, because these two are the examples of a nucleophile, right? And they are found to be an electron-rich species, right? And they are also electron-donating species, right? And how it is affecting and how it is influencing what? The biological activity that we have seen, right? Coming to this alkyl or cyclohexyl or aromatic system, right? We have seen when a particular system is having aromatic moiety in it, or cyclohexyl in it, or any aliphatic hydrocarbon in it, how it is influencing the biological activity by dint of its hydrophobic property. So it is an example. So it is defining the hydrophobic property, right? Like if we just increase the number of carbon, or rather if we just orient the carbon in a particular system in such a fashion so that it can produce a sterically bulkier things, okay, and then there we found that how this shape is influencing the biological activity, right? So that means what all the examples that I have given to you, right? So each and every examples, they are holding certain properties, right? And with that property we can correlate that property with this biological activity, okay? That means the property we just relate to biological activity, right? Now the thing is that sometimes it can happen that while dealing with a Hansch equation or while performing Hansch analysis, it can also be found that some entities which are being a part of a molecular skeleton, they are influencing the process of biological activity. They are influencing the biological activity. But with the help of a conventional parameters, we cannot determine the contribution which they are providing. Okay? That means those substituents cannot be defined with the usual parameters. In that case, but still they are contributing, no? That means exclusion of those contribution from the final equation leads to a partially correct Hansch equation, right? That we are not expecting. Nobody is expecting that you are okay. You can develop a Hansch equation, but at the end of the show, it has been found, it has been observed that a particular substituent placed at that particular corner was ignored. So in that case, we can say the Hansch equation was found to be an incomplete one, right? Okay. So make it meaningful. That means to include those contribution in the final form of this 2D-QSAR, right? Free Wilson, okay, they developed a particular process or technique through which we can at least figure out the contribution of unusual substituents, and those substituents are nothing but indicator variables, right? So that means the contribution that a substituent makes to the biological activity, okay, and moreover the contribution cannot be defined with usual parameters. That time we are just taking the help of Free Wilson approach. And let me tell you one thing, though we are not in a position to define that for what the contribution is coming, for what we are getting the contribution, but still it is quite often included in Hansch equation. Therefore, we should not ignore the contribution of what? Not the substituents, but the contribution of this scientist towards making the 2D-QSAR more extensive and more informative, right? Chalo. Now the thing is that let us just deal with this Free Wilson approach. Okay, what exactly, how the contribution is determined and all, let us see. So what happened here, the Free Wilson approach, here also they are just relating what? They are relating the so first and foremost, they're just taking a particular standard drug, right? And they're just making an analog of that particular drug, right? That means we have with us a template drug that we are considering as a template compound, and after that later on we are just making what? The substituted analog of that particular template. So we have with us what? The biological activity of the template or the standard and the substituted analogs of that particular template, right? And with this we are just relating this informations, okay? We are just relating the property, the unusual property, the unusual contribution to the biological activity. So that means a pool of compound has to be made. At the same time has to be made considering the template compound, that means the standard compound. So here biological activity, we are just relating the biological activity to what? To the standard and its substituted analogs, right? So how the equation will be? The equation will be something like log 1 by C, or rather you can also write biological activity, right? That equals to K1x1 plus K2x2 up to Kn(xn). So this is how the equation stands, right? Now let's just deal with the different things which are incorporated in this particular equation, right? We don't have to say anything about this log 1 by C because starting since inception we are familiar with this log 1 by C term, right? Okay. Now coming to this K and X, what exactly it means? Okay. So X means what? The substituent or the indicator variable, the unusual substituent for which you cannot figure out that contribution is coming because of what. It is because of what they are contributing. It is because of which property they are contributing. That cannot be figured out, right? Okay. Now Xn till Xn, right? We are considering that n number of substituents are there in a particular compound in which the actual property is found to be unknown. Okay, in that case, so suppose we have several substituents are there, and mostly they are found to be unusual. Few are there which are found to be usual, right? Okay. Now X, the n can be 1 or 0. That means if n is found to be 1, that means the substituent is present. That means the unusual substituent is present. If n is found to be 0, then the unusual substituent is absent, right? And what about K? K is the contribution that the substituent make to the activity. The contribution that the substituent, if being present, makes to the biological activity. Got my point? Chalo. Now, so this is how the equation stands. I am not done yet. Plus Z. Z is found to be the average activity. The average biological activity, right? Okay. Chalo. So now, this is found to be the equation, right? Equation. So with that we are done with what? With that we are done with that what exactly they are doing in case of in this Free-Wilson approach and all, right? Free-Wilson approach. So here basically the contribution of unusual substituents, okay, they're just trying to determine the contribution of the unusual substituents, and they're just relating the contribution of unusual substituents to the biological activity, and in that they have included what? The average activity as well. Average activity as well, right? Okay. Now, the pros and cons, the thick and thin of this Free-Wilson approach, right? See, the advantages, wherever a substituent cannot be defined with a specific property, that time we are just taking the help of this indicator variables or Free-Wilson approach, because it is meant for what? It is meant for determining the contribution of unusual substituents. So this is found to be one of the advantages, right? Okay. And the second thing, let us just move to the disadvantage, right? Okay. Now each K1, X1, K2, X2. Okay. It means what? That you have to come up, you have to develop a particular analog where not only the substituent but also their position need to be varied. Got my point? So each K1, each term indicates that you have to deal with a particular compound in which you have to vary the substituent. That means the pattern has to be varied. At the same time, their position need to be varied. Now, coming up with such a huge pool of compounds is next to impossible. Next to impossible. The huge compound. Suppose as I said that K1, X1. It means what? That means you have to come up with an analog. Suppose we have something like this COOH, right? This is found to be the template one. And with it you are just connecting what? X. Suppose X is found to be the unusual substituents, right? Okay. So this is for K1, X1. When you are in K2, X2, the X has to be converted to Y. And when you are in K3, X3, the Y has to be converted to W, like this, right? And in other case, the same W has to be pushed next to this carbon. Next to this carbon. That means, as I said, the pattern as well as the position. So each K1, X1, it defines what? That means the substituted analogs should have a substituent, okay? Substituent which is different. Not only the pattern but also their position. So earlier the X was at this position. Now later on you have found, all on a sudden you have to develop a compound in which the X should not be here, rather X has shifted from ortho to the meta. So coming up with a huge pool of this compound, if substituted analogs, is found to be next to impossible, because all may not be synthetically feasible, because synthetic feasibility has to be considered. Okay, prior undergoing this particular analysis and all, the synthetic feasibility of each and every substituted analog has to need to be considered, need to be taken care of. Then only you can perform the analysis, because you have to arrange a huge pool of compounds in which the variation should be there. The variation with respect to their substituent, the pattern, the variation with respect to their position. Both should be taken care of. Otherwise, you are not supposed to incorporate that particular analog in the study. Got my point? Okay. And the second disadvantage is, so this is about the substituted analogs. Second is, at the end of the show, you cannot rationalize the determination. Why? Because you cannot say, okay, though you can predict, you can get the data of the contribution that the unusual substituents makes to the overall activity. But unfortunately, you cannot rationalize that what for the contribution is coming. The contribution is of which property, that cannot be unfolded. So that means you cannot expose the property for which the contribution is emerging. And ultimately, this is related to this biological activity. Okay, these two are the disadvantages of what? Free-Wilson approach. Okay, so we are done with what? We are done with this Free-Wilson approach or indicator variable. Now let us move to the next one, that is the final form. That means Hansch equation. Okay, as I said, Hansch equation is found to be the final form. And I said earlier also that in case of 2D-QSAR, basically we are dealing with what? An innumerable descriptors, right? Around 3,500 descriptors. okay, which have already been discovered, right? Okay, but in case of in Hansch equation, basically we are dealing with what the commonly used variables, the commonly used descriptors, like your hydrophobicity, like your hydrophobic descriptors, like your electronic descriptors, like your steric descriptors, and sometimes the free Wilson, that means the indicator variables as well, right? Now let us see that how the final form will be. If the number of descriptors, or rather, as I said, the usual properties are assembled there. Okay, the usual properties or the usual parameters, the parameters which are quite often used. Okay, they are being brought in dealing with the Hansch equation. Okay, now in the process of deriving the Hansch equation, we are just we are considering what the usual descriptors or the descriptors which are quite often being used. They are found to be hydrophobic, electronic, steric, right? If we if we are talking about this hydrophobic descriptors, then pi comes into play. Pi comes into our mind, right? The second one is your log p comes into our mind, right? If we are just dealing with this electronic descriptors, the sigma will come into play, right? The sigma definitely not, right? And if we just mean to say that steric descriptors, it is sometimes Stubbs steric factor, or we can say molar refractivity. Okay, so these are the few descriptors, okay, that are being quite often being chosen in deriving the Hansch equation, right? Okay, so now the thing is that let us just deal with the first one, log p, one of the essential criteria, right? I should not say the only criteria with which the drug is exerting its action and all, but the thing is that it is one of the major criteria which has to be taken care of while dealing with basically the centrally acting drugs. Okay, because in order to become a centrally acting drugs, the drug first need to cross the blood-brain barrier, need to access the lipoidal section of a particular system, living system, and then only it can be permitted to get into the active site, to reach the active site, right? And for that, it should have a substantial level or substantial value of log p, right? Okay, chalo. So what they found that if log p value lies within the range of 5, that means if we are just dealing with a narrow range of log p, okay, in that case, the Hansch equation, you can find a linear equation. You can find the linearity when the log p lies within the range of lies within a narrow range, right? Narrow range. In that case, the graph will be linear. You can find a straight line. That means the linearity exists when the log p value lies within the range of 1 to 5, right? Similarly, if the log p is crossing the limit, that means it is say for example it is well scattered. Well scattered means it is widespread. In that case, the linearity will get lost, and you can find the equation exhibits a parabolic curve, right? So with this equation, that means a parabolic curve obtained when the log p lies or log p crosses the normal limit, right? But when the log p value lies within the narrow range, in that case you can find the linearity, right? Which will eventually get lost when the log p exceeds the normal limit, or rather when the the range is found to be a broad, right? Okay, now that we found long back while dealing with this log p determination or substituent hydrophobicity constant, okay, determination, right? So how the final form will be? Let us deal with the final form of this Hansch equation. So how it will be? Consider that the log p value is found to lie within a narrow range. In that case, you are supposed to get a linear equation, right? So that means log 1 by c equals to k1, then k1 pi plus k2, say k2 sigma plus k3 es plus k5, okay, like this. And just on top of it, you just write, as I said, substituent constant. As I said, log p, that means log p should be included, right? Should be included. Let us just make it k2, k3, k4 and k6, right? So that means k1 log p should be on top, plus k2 pi plus k3 sigma plus k4 es plus dot dot something like k6, right? So this is the final equation. This is the final equation. Final equation of what? When the log p lies within a small range, you can get the linearity, right? But the moment you'll find the log p is well scattered, or we can say it has exceeded the limit, okay, the limit has been exceeded, in that case the equation, there is no linearity that you can observe in the equation. In that case, the equation, how the equation will be, the equation, there is a change in the equation, right, and the change is nothing but log 1 by c equals to minus k1 log p whole square plus k2 log p plus k3 sigma plus k4 es plus dot 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 something like this, and finally k5, right? And all this k term, the constant and all, you can get this, the computer itself will generate the value of this constant and all, right? You don't have to bother much about this, right? All the things will be determined by the computer only, right? Okay, so now this is the final equation, in which case when the log p is not lying within a small range, right? So that means the log p has to lie within a small range, then only you can find the linearity. But when the log p exceeds the limit, in that case you can find the graph like this, parabolic, okay? So it is a parabolic relation, okay? So this is found to be the final form of what? Hansch equation. But as I said earlier, that they are taking, or they have developed, they have discovered n number of descriptors, okay? Those are also been incorporated in Hansch equation. But in Hansch equation, basically we are dealing with what? The descriptors which are being quite often being studied, okay? That means this is found to be the usual parameter, right? This is found to be one of the these are the key parameters, right, with which a drug can develop its biological response, right, or the drug develops the biological response, right? And that is why these terminologies, they are being brought in the Hansch equation. So with that we are done with what? Hansch equation. Now, so that's all about your 2D-QSAR and all, right? But now let us deal with the advantages of 2D-QSAR, right? Now, just let me just spare another few minutes, right, in dealing with the advantages and all. Basically, in case of this 2D-QSAR, you don't require any kind of receptor and all, right? That means you don't have to seek the three-dimensional, the crystallographic structure of the receptor. Why? Because 2D-QSAR does not belong to what? SBDD, that is structure-based drug design. It's a macro, it's not, it does not belong to macromolecule-based drug design. It's a structure-based drug design, but small molecule-based drug design. So that is why you don't have to bother about collecting or fetching what? The crystallographic structure of what? The protein or the receptor. So that is why this is found to be one of the advantages, right? Now let us deal with the disadvantages. Why? Because in my next video, definitely I'll come up with the 3D-QSAR and all. So that means why 3D-QSAR came into play, came into existence. That means there must be some kind of lacunae, some pitfalls definitely were there with this 2D-QSAR. That is why they brought another, they just added another dimension into that 2D-QSAR to make it 3D-QSAR, right? Okay. So in that case, we can say that there are several disadvantages there. Okay, what are those? So first and foremost, in case of 2D-QSAR, compounds with similar structures, they are being taken into consideration. That means what are the compounds that you are collecting to initiate the process of 2D-QSAR. That means I told you long back, in be it 2D-QSAR or 3D-QSAR, first and foremost you have to collect what? N number of compounds, right? That means the n number of compounds which are already been synthesized, chemically characterized, at the same time biologically evaluated. That means you have to have what? The structure of those synthesized compounds along with their biological data. With that two things, with these two things only, you can initiate the process, right? So, and the second, that means while collecting the compounds, you have to closely monitor that what are the compounds that have included. I'm going to consider for the study, are they having similarity? So that means the compounds with similar structures need is basically the need of 2D-QSAR, right? So 2D-QSAR always demands what? The compounds which you are going to consider, they should have similarity. Okay? Okay, amongst each other and all, right? Okay. The second thing, so this is found to be one of the limitation, right? The second thing, 2D-QSAR, okay, it does not directly suggest you to synthesize a novel compound. Is it really possible? Suppose the equation is there in front of us. Okay, any one of you take the challenge. Okay, with this particular information, from this equation, can we get some idea that how a particular novel compound can be designed? No, it's not like that. That means the equation should not directly suggest us, okay, that the equation, it is not at all suggest us that what compound should be synthesized and what compound should be designed and subsequently synthesized, right? So that means dealing with this equation, it will take more time, right? You have to spend quality times with this equation, then only you can at least develop the understanding, and with that understanding only you can exploit the understanding to come up with a design, right? So that means it's a time taking process. It will not directly suggest us to synthesize some compounds and all. That means it will not say anything about the compound which has to be designed and subsequently synthesized, right? Now, few more are there, like disadvantages, like your suppose in case of 2D-QSAR, so here you can readily observe here that we have incorporated what? The sigma and ES. While dealing with this sigma and ES in my past videos and all, so there we found that how this sigma as well as ES, those values we can get. And in order to get those values, we need to monitor what? An equation, right? Equation means, not equation, rather a reaction, right? And there we have to focus on what? We have to focus on the rate constant. How the rate constant is affected by the substituent. That means we were bothered about the equilibrium constant. An equilibrium can be destabilized or can be influenced some other properties. Not that only ES is acting on it. That means whatever change in the rate, that is not solely because of ES. It may happen. It may happen because they are usually taking into account rate constant. The rate constant the rate constant should not depend on a single criteria. It may be influenced by multiple criteria. And when the latter case happens, then definitely the ES value should not be the right one. That means it's an admixture of what? The other properties. So in that case, the equation is found to be a false one. Because here you are supposed to get what? You are supposed to get steric contribution. But as the steric contribution is affected by the electronic contribution, so that is why it's an admixture of property. No longer it's a sole steric property. Steric property is mixed with the electronic property. So this is another disadvantage. As the most of the descriptors, they are relying on what? The rate constant, considering the fact that the rate constant should not always depend on a single criteria, should not always depend on a single factors. So multiple factors are affecting the rate constant. So that is why chances are there that you can get a false negative or false positive data, right? So that means there is a false data that you are going to incorporate in the Hansch equation, and finally the equation will prove to be wrong, right? This can happen also. So this is the problem. This is another disadvantage, right? Now coming to the other one, that is see, dealing with a mathematical equation and developing a particular compound is very tedious. It's very extensive and tedious, right? For a chemist, it's very hard to unfold the mystery that is there within this particular equation, mathematical equation. So, dealing with a mathematical equation and subsequently develop a chemical, formula or chemical structure is found to be a cumbersome process, what we can say. It's a cumbersome process, right? And the final one is, sometimes it has happened, say for example, while looking at this particular equation, can we find any kind of unusual descriptors here, unusual contribution? So assume that while framing this particular equation, we have forgotten what? We have forgotten to include the entries of unusual substituents. So that means we are left with another contribution which was not incorporated here mistakenly. It was by mistake we forgot to incorporate the contribution of unusual substituents. So that means the final equation may not include the entries of unusual substituents. So these are the few disadvantages of 2D-QSAR, and that is why in my next video I am going to launch another thing, that is 3D-QSAR. So with that, I am concluding today's topic. Hope you liked this video. Now, if you have any queries, if you have any, put your comments, okay, put your comments so that I can go through those comments and deal with that comments. And say thank you for your patience hearing and all. If you like this video, don't forget to press the like button. Thank you so very much for your patience hearing. Thank you.